Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our calculus series. So previously we talked about, we talked about the first one, or Taylor Notes section one. And the idea behind this concept was that, okay, if we're given some function, we have to find an estimated sort of graph, right? So we have to estimate based on some given b. We call this, or we estimate using a line, and we call this a linear approximation of the curve at that particular x value, which is b, or we call it a tangent line approximation, or we also call it a first Taylor polynomial, right? So it helps us sort of estimate what the behavior is or what the value is at that point, given a line. And then we can also use that to estimate an error. Now, I did not discuss too much on section two. I kind of did it on my own. But the idea behind section two is instead of it being a linear approximation, it's more or less a quadratic approximation. So how does that look like? Well, let's say if we have some curve, or let me go to section three. Let's say if we have some curve here, right? A linear okay, let me just do this. So let's say we have this, right? That's our curve. This is our x and y axis. This is the plane curve. And let's say we want to find the value of this thing here. This is x equals b. And so this is our function f of b, which is the same as y. And so here we have b, f of b as our pair, our ordered pair. And the way we can estimate this is to use a tangent line approximation or a first Taylor polynomial. So how do we do that? Well, we can say, okay, probably looks something like this. Right? And this is our first Taylor polynomial, which is equal to a line. So it's an approximation, right? So this is, or in other words, let me just do it like this. This is sort of f of x, but it's approximately a first Taylor polynomial, which is just my derivative at b, x minus b, and then we add it to f of b, right? And so this is basically how we can get an approximate value as we approach b using a line, right? So that was section one. Let me, oh, that's weird. There we go. Okay. I couldn't, I couldn't move the thing. Okay. So we have this. Okay, this is in section one. Right. So, okay, it's been a while since I've made videos, and I'm actually in a new room. Funny enough, I'm not in my dorm. So yeah, that's also another thing that's new. I don't know. I think the when I watch this recording, the voicing might be weird, but anyway, it's cool. So really, here we talked about first Taylor polynomials, how we can use that to approximate values at some given x value, right? Okay, now in section two, which I haven't discussed because I think it's quite easy to say. I mean, there's really not much to say, but let's say we have the same thing, right? We're given the same plane curve, the same, okay, maybe not. I can't maybe draw it the exact way, but something like that, right? So that was my plane curve. Again, we're in my x and y axis. And again, I'm trying to find an estimate for this is x equals b. This is f of b, which is around y. And so there's the point b, f of b. Or let me write it this way. B f of b. There we go. And so now what's the difference with our approximation? Because we can't really approximate using lines forever, right? There are more accurate ways to approximate these types of stuff. And so maybe a more approximate way of doing that is using a quadratic approximation, or we call it a second Taylor polynomial, right? So it would probably look, okay, I'm going to be honest, I'm not sure, but something like this maybe, right? So this is more approximate than using a line. And so we can say again, this function is approximately my second Taylor polynomial, which is just my first Taylor polynomial plus a half, or we call this a factorial, and then a double derivative, and then x minus b squared. Or here we put an absolute value. Am I right? I think I got it right. Hopefully. If I didn't, then that would have been messed up. I'm just double checking. Oh, so this one's b, right? So this one's supposed to be b, right? So that was pretty much section 2. It's basically a more accurate approximation of a linear approximation, right? So this is basically linear, and this one's quadratic. Okay, now for the next one, now we actually go to section 3. And I think this is a more general idea of what exactly is. So here we're getting more and more into the Taylor series. Okay. So let me go ahead and look for the example. Oh, where is it? Oh, I'm not in the, okay, there we go. Now we move on to section 3. And this is basically, okay, well, I'm gonna write the title, obviously. It's the higher order approximation. And Taylor's inequality. No, I'm not sure what that is yet. I'm gonna see it. We're gonna see what this is in a bit. Okay, so in this section, we will extend the ideas of the two preceding sections to approximations by higher degree polynomials. So pretty much the ideas are the same. But first, let's introduce some notation to make it easier to describe the results. So let's say we have n factorial. So here we're introducing this idea of n factorial, which is n minus n times 1, n times 2, n times n minus 2, all the way to 2, 1, right? So here we're going to introduce this idea of factorials. And I did kind of cover it in a bit, but the idea behind factorials is, let's say we have a 4 factorial. This is 4 times 3 times 2 times 1. We have 5 factorial. This is 5 times 4 times 3 times 2 times 1. And that's going to give us sum total. So this one's 12 times 2, 24 times 1, 24. This one's 20 times 3, 60 times 2, 120 times 1, 120. And so that's the idea behind n factorial. So n times the number minus 1, and then the number minus 2, and then so on and so forth until we reach 2 to 1. So that's what a factorial is. And it's basically the product of the first n integers, right? So we call this idea n factorial. And it's the product of the first n integers, right? Also, now let's introduce another thing. We have f k x. Now, what in the world did I just write? This is, or denotes the kth derivative. So if I put a 1 there, that's the first derivative. If I put a 2, or in this case, we actually don't put 1 and 2 as in the numbers. We put like f prime, and then we go to f double prime. Triple prime, we even do that. But the moment we get to 4, we do the number 4. Or we get to 100, we do 100. Right? So that's the idea. So that's the kth derivative of f at x. And if we integrate this equation by parts again, so if we remember from 2.2, what's 2.2? Probably something from here, which I haven't discussed in a bit. 2.2 is, let me see, 2.2. Okay, cool. I can't really. Anyway, I'll not say that again. So if we do a by parts, what we're going to say, my function is equal to, so this is my first Taylor polynomial, which is just a linear approximation, right? This whole thing is t sub 1 of x. And then when I add it to here, which is my second derivative at b, not at x. No, I square this. This whole thing is now t sub 2, right? My second Taylor polynomial, which is otherwise known as a quadratic approximation. And then I continue on. So I do 3, whoops. So now I do a 1, 3 times 2, f triple prime at b, right? So we can kind of see the pattern here, x minus b to the third. And then what do you think is the next thing? 1, 4 times 3 times 2 times 1, it's fine. F to the fourth, b, x minus b to the fourth. And then what's next? 5. Or well, we don't really. Anyways. But yeah, we keep on going. Oh wait, shoot, my bad. I meant for the 3. Yeah, it's gonna be a 3 here. Let me just do 3 instead of the. So that's the 3. And then for my 4, well, it's gonna be. Oh, this is actually gonna be 3 times 2. Whoops, my bad. 3 times 2, fourth derivative, and then some t value, right? Okay, I think I've gone far ahead. So t, and then this is a t, this is a 3. There we go. And then dt. So this is what we integrate. Okay, and then this would be this x. It's fine. Yeah, so we integrate this thing, and then dt. There we go. And so what happens when we integrate this? Well, we can take this out. The 1 over 3 times 2, right? We can take that out. This one, well, let's see. Okay, so let's make it more general. So basically the high level idea behind this thing is f of x is basically from this plus this plus this 1/2, right? Double prime squared plus the third 1/3 times 2 f triple prime, right? And then my final thing, so I keep going. This is going to be 1/n factorial, right? So that's somewhere in the middle, n factorial. So this is f of n, nth derivative, x minus b to the nth, right? So that's that general pattern, and we keep going. So towards my end, it's going to be still n factorial, and then we integrate this f to the n plus 1 t x minus t to the power of n dt, right? So it's just this integrating, but we can see the pattern, right? Yeah, so that was a more general idea of what we just did. Okay, let's do a formal definition of what in the actual thing am I talking about. Okay, so the nth. So now we're talking about something more general, right? Because we could get a first Taylor polynomial. We could get a second. We could get a third, a fourth, a fifth, a millionth, an nth. So that's a more general idea there. So we're gonna get the nth Taylor polynomial for f based at b. Is this below? So you have t to the nth x. So the nth Taylor polynomial, which is f of b plus its first derivative plus. So instead of 2 times 1, what is this actually? It's 2 factorial. Now let's write it in a nice way. F, so this is the second derivative. I'm not writing the apostrophes because I'm trying to emphasize that idea. And this is 2. And then we keep going. So we keep going until we reach the nth. So the nth, and there we have it. And so there are a lot of symbols in the above formula. I mean, we can kind of see there's a lot, right? But keep in mind that x is a variable and base b is a fixed number, right? So b is some number, and the nth Taylor polynomial has terms, which are numbers, and they're actually called coefficients, times powers of x minus b, right? Okay, I hope that makes sense. And now, since what we've been doing in the previous Taylor notes, Taylor notes, is once we get some approximation, some Taylor approximation of the curve, now we want to bound the error. We want to get the error bounds. And we have done that for section 1 and 2. So in section 1, if I remembered correctly, so error bounds. In section 1, we talked about how to get the error bounds of a first Taylor polynomial, and that's this formula. F of x, t sub 1, less than or equal to m half x minus b, so that b thing squared. Let me see if I got that one, because I feel like I don't remember. Yeah, okay, so I did, yeah. So that's the idea. Oh, this one has to be an absolute value, because we're not sure if b is a positive or negative value. We're not sure if this thing's positive or negative, but we want to make it positive. The errors, as much as possible for errors, we want to make it positive. So that was that. Now in section 2, which I did not discuss in depth, but I'll go to it just in a bit. It's the same idea for the most part. So it's this m divided by 6, x minus b cubed, right? Oh yeah, for here we want to calculate, so again, from our previous discussion, the absolute value of the second derivative to get our m. Here we want to calculate the third derivative to get our m. So it's kind of like this and this. Now, what if we want to make it general? Here's the formula. So just by observing this idea, so in general, the error bounds of our nth is what? This is 2, this is 6, this is 1, this is 2. I can't really make a difference there. But it's basically, funny enough, it's actually m n plus 1 factorial. So if our n was 2, we add 3 factorial is 3 times 2 times 1, which is 6. Yeah, I mean, even I couldn't see that. I'm just looking at the text. 1, right? N plus 1 factorial. So 1 is n, 1 plus 1, 2. Get the factorial of that. That's 2 times 1, 2. So that's the more general formula for an nth Taylor polynomial. And then we go x minus b, and then we go, what is this? 2, this is 3. In our first case, 1, this is 2, so it's n plus 1. Right? At least I could see that. Hopefully. I hope it's not like some complicated formula. But that's the idea, right? And now, how do we get our m? That's the other thing. Well, it's going to be f. So again, this is 2, this is 3. 1, this is 2, so it's f to the n plus 1. Then this is, I believe, x less than or equal to m. So that's the general stuff, right? And that works for all x in that ith interval, where t sub n is the nth Taylor polynomial for f based at b. Don't worry, I just read all of that. Okay, so, right. Okay, let me see if I have to point this out. I don't think I need to. Okay, I'm not gonna look at that anymore. So we did try to prove when x is greater than b and when x is less than b. But in these examples, I don't think we need to bother. Yeah, I'm not gonna, yeah. Okay, so maybe let's look at a few observations, right? When we look at a tangent line error bound, so in section 1, that's when n is equal to 1. So actually we say the tangent line error bound is just the Taylor's inequality when n equals 1. The quadratic approximation error bound is the Taylor's inequality with n equals 2. So when we were talking about error bounds, right, we talked about the tangent line error bound. And then the next one, of course, it's a quadratic approximation error bound. More generally, for an nth Taylor polynomial, we call it the Taylor inequality. And that's pretty unoriginal, right? Inequality. Or shoot, I'm referring to the wrong one. I meant this one, right? Inequality. Inequality. Yes. So we call it a Taylor inequality instead of an error bound. Okay. I'm not gonna. Anyways, I'm not gonna go through that. Okay, so let me do an example. No, I chose green. What the? So here's our example. So 3 So suppose f of x is equal to 1 over 1 minus x. Right? So that's our function. Okay. We're being asked to find, so not the first, not the second, but the nth Taylor polynomial. Or in other words, we call it t sub n of x for f based at b equals 0. So how do we do this, right? Because now we're finding a more general thing. So here, well, yeah, so from our previous videos, right, we're finding t sub 1 and then t sub 2, but pretty much the steps are the same. Here we're finding t sub n. So the first thing we want to do is to find, well, yeah, we want to find the derivatives, right? So we want to find the derivatives. So we want to find f. Okay, so we want to find f of x, f prime of x, f double prime of x. We keep going. Or okay, sure, maybe even f triple prime. But the idea is to find a pattern. So we want to find some pattern. Okay. And we're not going to refer to some formula. Or actually, I think we should. Yeah, it's this one. This is the formula. So so here really I'm just highlighting what I think is useful for and this is the other thing that we want to look at. There we go. Okay, so find, well, we have f of x. We already have f of x, which is 1 over 1 minus x. Now, how do we find, there's a quicker or a more convenient way of writing it if we're taking derivatives, and it's actually, and I haven't done this in a while, I'm surprised I didn't notice it, but it's 1 minus x to the negative 1. Right? And if you take the derivative, instead of doing a quotient rule, you just do, you just put this down, subtract 1, chain rule, done. Right? So let's try it for the other derivative. So let's try f prime of x. So we take the derivative of this thing, which is just minus 1 minus x. This is now minus 2. And then we have a chain rule. Chain rule is this thing, so that's minus 1. So actually, it's just 1 minus x minus 2. And we can rewrite this as 1 over 1 minus x squared. And then let's keep going. F double prime. So now we take the derivative of, I'll do this one, right? So this is minus 2, 1 minus x, minus 3, chain rule, 2, 1 minus x, negative 3, 2 over 1 minus x to the third, right? Let's do another one. Third derivative, minus, or no, not minus 6. Oh yeah, minus 6. Alright, let's just go for it. So 6, 1 minus x, minus 4, 4, okay, no, I messed up. 6 over 1 minus x to the fourth, right? So what's the pattern? That's what we want to find. So what if we do f of to the k? There has to be some pattern, right? What's happening to the, so we always have a 1 minus x. That's one thing. we have, okay, what's happening here? -1, -2, -3, -4. Something that has to do with this k. This is 1, this is -2. This is 2, this is -3. It's something linear, right? So this k, this is 3, this is -4. What do we notice? It's minus of k plus 1, right? So it's 1 minus k. That's the pattern there. Now for the 6, am I right? Wait, let me see if I got that one. Oh, okay, so what he did was, yeah. Minus k minus 1. Oh, shoot, this is -1, really? Okay, let's try. So we have k, say that's 3. 1 minus 3 is -4, right? See if I got that one. Whoops, my bad. So it's minus, yeah. So it's -1 minus k, or minus k minus 1, doesn't matter. And then for this -1, -2, or shoot, this one, and then the 6. 1, 2, 6. What is that? Factorial, right? 1 factorial is 1, 2 factorial is 2. 3 factorial is 6. So we want to relate it to the derivative because that's our general case, our k. We want to relate everything that we find to its derivative. So this numerical coefficient here is going to be, so this one's something related to 1 and 1. First derivative and 1, 1 and 1. This one's related to 2 and 2. So 2 and 2. And then this one's 3 and 6. Oh, it's a factorial. 1 factorial is 1. 2 factorial is 2 times 1, 2. 3 factorial is 3 times 2 times 1, 6. So that means k factorial, right? And so that's the idea. That's the pattern that we want to find. Okay. So we have, oops, what am I looking at? What is this? The coefficient of x minus 0 to the kth. Huh? What am I looking at here? Okay, so okay, this is a textbook, but it says something about finding f to the kth when I plug in 0. If I plug in a 0 to my x, it's gonna be 1 minus 0, some k value. It's always gonna be a 1, so it's just gonna be k factorial. And then the coefficient of x minus 0 to the kth in the Taylor polynomial is just f. So this thing divided by k factorial, which is essentially 1 because we know this is also k factorial. Oh, okay. And then from there, well, now that we know this, my nth polynomial is actually 1 plus x squared plus x to the third all the way to nth. Right? Okay, I hope that made sense. It didn't make sense for me. when I got to this point, I'm like, what? Why do that? Wait, let me backtrack a bit. I want to see what's happening. Okay. After the kth. So that's, what is that? Yeah, it's after the cave, and then this is an X question mark. Yeah, this one makes sense. And then when I get to here, I plug in a zero, this makes sense. And then the moment I find maybe this were, that's funny. After the kth of zero divided by this is a one. What's happening? Yeah, because I keep going. Hmm, this is weird. K. Oh, let me try something. So once I get this, I want to do a summation. Let me do a summation. My k starts at zero. I go all the way to n. And so that means my derivative, my x, or actually, yeah, that's fine. I can rewrite it. This is k factorial 1 minus x. There we go. 0 factorial is a 1. This thing is a 0. This is weird. Okay. So the idea is once we get some pattern, you want to remove this. And then you want to get to this thing here. The idea is to get to there, but I can't seem to wiggle my way there. K factorial is 0, 1, 2, 3, 4, 5. Or I could just plug it in. And maybe that was the plan. Maybe not a summation. Maybe I'm just making it confusing. I just plug in something for 0. And I would get something like k factorial 1 minus 0. Then really anything here is just 1. Or this thing is 1, so it's just k factorial. And then the moment... What? This is weird. And then I divide it by my k factorial. That's funny. Oh wait, let me try this. I'll ask GPT, see if what they can do here. Just test the AI out. Okay, I can share you my. I'll share the screen. This is GPT. They have a name for it. Maclaurin geometric series. Oh, he got it so quick. What in the world? That is quick, crazy quick. Oh my, how's the? That's fun. Okay. Wow, he even did a. That's. Wait, so first thing, I can't even see what I'm typing because of the chat thing. Wait a minute. I'm gonna move this. There we go. Moved it there. So the first thing we took, and we took one, two, three, each derivative for some case derivative. Yeah, and then I'm gonna ask it what do we do from there? Oh, you could annotate here? That's crazy. Okay. So I plug it in all the way to nth, right? Okay, my intuition of summation might be right, but again, I'm not. Mhm. Do I start when x is 0? That's the thing. Mm, okay. Okay, so I feel like it's more of the pattern finding that's making this a bit off. Anyway, okay, let's see how far we can go. So, so now that we've found this formula, we want to put it in some summation, right? That's weird. Or I want to put when 1 is 0. Or, no, what am I saying? When 1 is 0. Oops, I turned off my camera. Okay, so, uh, I mean, sure. You know what? Fine. I don't think it matters too much. Wait, once I get the K, what do I do with the... Okay, there might be an easier way to look at this from this view. So, okay, this could be... Let me see. Oh, where are we based at? When B is 0. So when B is 0, I have to make it such that will be 0. So x is b, b is 0. So I have to start when this thing is 0. And so I'm going to get some k factorial. Okay. I think that's what it wants me to do. Okay, so after finding the pattern for the k, now we want to... So we want to find f of k at b, right? Because that's where we're based at. And so that's going to be... So f 0 is basically k factorial. This is k factorial. Right? And then once we find that, once we find where we're based, now we want to start at k equals 0 and go from there. Okay, I think I'm a bit lost. So after this, we want to... It's so confusing. I just realized how confusing it is to find the pattern. It's not a simple task to find patterns unless you're really good at it. For me, I'm not. Anyways, so okay. So the first step is to differentiate, find some pattern, and then we do the base thing. And then we evaluate at 0 because that's where we're based. Okay, you know what? I don't think I get it too much for now, but now I think we can, let's skip this a bit. So basically now our Taylor polynomial is some summation from starting from k0 to n. We do f of k of 0, k factorial, x to the k. And so that's basically, since this is 1, this thing is 1, and there we go. Now we have 1 plus x to the first, then x to the second, all the way to x to the nth. So that's the Taylor polynomial. Okay, I'm not gonna dive deep into it. I feel like I'll do more variations of this, maybe get the idea. Okay, there's like a long, geez. Okay, one more example, and then we should be good to go. So 3.2. So here we let our function be e to the x, right? So an exponential function. First thing we want to do is find the nth Taylor polynomial. Heck, I might even do some exercises after. We'll see. But I feel like the video is taking too long. So that's t sub n of x for f, our function f. And I might show a graph after at b equals 0, right? Okay, and then the other, okay, so the other ones are more in error bounds. So I'm going to focus on this first. So first we find a pattern. Okay, so keeping in mind, maybe our mathematical tools that we can use is taking derivatives, factorials, right? That's the hints. Those are the hints. So more on, when we find a pattern, we look at derivatives and as well as factorials and maybe something else that we can sort of see. But this one doesn't have a definitive step to it. It's more or less us finding some pattern, even with addition, subtraction, and stuff like that, right? Okay, cool. So let's just go for it. So f of x, you know what's funny? These are all the same. F prime of x is this. F double prime is this. So that means my kth doesn't really matter because it would just be e to the x. So that's the funny part. So we didn't really, it's not much of a hard work here. Okay, cool. So now that we've really done the work and found the pattern, well, okay. Now let's, yes, that's the pattern, right? Now the next thing is to, okay, let me see. Now we have to find where it's based at. So at B. Where is it based at? It's based at 0. This is e to the 0. This is 1. For all k and all x. So that means my t sub n. Trying to do a summation here. Trying to get the hang of summation. So k starts at 0 all the way to n. Then we say this is this thing. My function, right, at k, or my kth derivative. I mean, is it like this? I don't think it's like this. Well, let me see. Actually, no, let's not do something here. Hmm, wait a minute. Oh, shoot. Okay, this is fun. So, okay, I'm still trying to figure this part out. How do we find, so what? Like, how do we find, so of course we start at 1, because I put my x as 1, my x is 0, and then when I do 1, oh, what do I get? Ah, that's funny. Oh, crap. Because there isn't a pattern that we could, like, follow. Where in the world did he get? Yeah, I'm stuck here. I'm stuck specifically at this part. I thought I could get away with it using. I'm gonna look at AI again, see if we can. The thing is, we want to find some pattern of the steps, at least, on how we can. Oh, there is a Taylor formula that we could use. Let me Google this real quick. Fna x minus a. Right. So we do have a Taylor formula that we could use. Funny enough, we actually do have a Taylor formula. Oh, shoot. I did not know that. Yeah, we have some formula we could use. So there's a reason why. Okay, it's kind of hidden. Like I just Googled it. So we find this, and then we use the Taylor formula. Okay, don't tell anyone. I just Googled this up. So Taylor formula. And this Taylor formula states that, okay, maybe even here, it's this thing. This is the Taylor formula. So the Taylor formula tells us, I'm gonna make it more catered to the course. It's gonna be some summation going all the way from n. K starts at 0. Then my base divided by some factorial, x minus b. Just xk, doesn't really matter. This is xk. Right, so that's that formula. Now let's actually apply it. This thing is 1. So actually, it's just x to the k, k factorial. And so if I start at 1, or at 0 actually, if I start at 0, 0 factorial, and then 0 of this is 1, I add this is 2, this is 3, 3 factorial, 2 factorial, going all the way to n factorial. Nice. So we got, yeah, that was the formula. Oh, there's even a different way of writing it. Oh my God. Anyway, okay, so that's the idea of writing that. Okay. Boom, we discovered it. Actually, let me show something. Well, I'm gonna go to Desmos. I'm actually gonna show something here. So if we go here, let's open a graph calculator. That's what my e to the x. That's e to the x. Now, what does a Taylor polynomial look like? That's y equals, say 1. Now I add squared over 2. Okay, cube over 6. Okay, getting better. To the fourth, over 4 factorial. Not possible. Okay. Let's go all the way. Maybe a fifth. 5 factorial. Or this, okay, this is 3 factorial. Let's keep going. 6 factorial. What's happening? Oh, shoot. I thought it out. Okay. Let me do, can I do a summation here? Oh, there we go. That's better. Okay. N 0. What was this? X to the, okay. I'm just trying stuff out. Okay, factorial. Let's add a slider n. So let's start at 1. Then as we're going, we're actually getting better and better stuff. Oh, 100 makes it really good. 3, 4, 200. Ooh, 35. Okay, I'm gonna stop trolling. So that's the idea, right? So when you go negative, that's pretty bad. But as we're maybe we need to play it out. Okay, I thought I was gonna, but yeah, it's that idea, right? And as we keep on going, we're getting better and better approximations until we go to infinity. No, it's undefined. Cool. It's 100. Yeah, so the bigger and bigger stuff that we have. Mm, it doesn't show. That's funny. But yeah, I guess the Desmos can't take it. Yeah. Anyways. Yeah, so that's the idea, right? Of the Taylor polynomials. We can try to approximate curves at a certain bound. Right? So we can sort of play around with these and with other functions as well, right? So that's the cool thing about Taylor polynomials is that we can do all sorts of cool things with it. And apparently it's for a probability course, so pretty excited about that. I'm gonna take probability next term. I'm gonna take linear algebra. But let's see. Okay, let's continue before I digress. So for B, so that was the idea. That's the answer actually. Am I sharing the right screen? Okay. Right. So for B, now we wanna do this. We wanna find an n such that, or so that, when I take the bounds, or we call it now a Taylor inequality. Oh, what is this? Tn, that's weird. Actually, it's the same thing if we think about it, right? Is less than 0.01 on some interval. J, this is -2 to 2. So how do we minimize that error? Or how do we get the error bound, right? So the way we can find this is we want to calculate the absolute value of some derivative. So I think it was, yes. So it's really the same steps as before, but we're just doing it in a more general sense. There we go. So you want to calculate that, and then you want to calculate m, and then you want to use the formula to get the error bounds. And then from there we can find our n value. Right. Okay, so let's just hop right into it. So to calculate this thing, What's our f of x? E to the x, right? Funny enough, this is, yeah, so if we get n, nth, what's funny is that this is all equal to the same thing. So if we take the absolute value of this thing, it's actually the same thing. So it's just e to the x, right? Because as we're taking derivatives, it's really it's the same thing. And then from there, okay, let's now calculate m. So let's use that formula. So on this interval between -2 and 2, which personally I think is a big interval, right? Let's see which one's bigger. Is this thing bigger or this thing? Well, we can say that. Oh, I'll use a calculator. E to the, funny enough, if they're the same, e to the 2 is 7.3. Oh, this one's bigger. So this one's less than this. So we're going to use e to the 2, which is equal to my m. Then from there, we'll use formula to calculate error bound, or we call it a Taylor inequality. In a more general sense, right? Okay. Okay. So from here, let's calculate the inequality. So what do we know? We know that, actually I highlighted this. It was somewhere here. There we go. So my f of x, or my e to the x, minus my Taylor polynomial, which is less than or equal to my m. Yeah, let's just play around with it a bit. T to the nth. My m is e to the 2 divided by n plus 1 factorial. And then what was the x minus b n plus 1. So now we're going to focus on this thing. N plus 1. Okay. And then I basically just plug in, right? So I plug in my b, which is, I believe, a 0. Yeah, so this is just going to be this thing. And then I plug in my x. So my x is in between those two endpoints. So on interval, -2 to 2. Well, that's where I plug this stuff in. Which one's better? This thing n plus 1? Or actually, funny enough, it's the same thing. Yeah, it's the same thing, right? If we plug each of these, it's just gonna be, so this thing here is the same as this thing. So I'll just call it this thing. And so I basically have this idea here. So f of x. So that error, or we call it Taylor inequality, but error bounds. And then this is e to the 2. Plop this in. Oops, my bad. I did not mean to do that. There we go. Okay. Nice. Beautiful. Kidding. Yeah, so that's that. And then, so what was the question again? We want to find an n. That's this. So now we calculate for n. That's the hard part. So when we calculate for n, oh crap. Shoot. So this is a guessing game. Oh, goodness me. It's a guessing game. So what does that mean? I try to plug in random stuff until I get something that's actually less than, right? So you want to get something less than. So we call this a guessing game. So this is where we pull out our calculator and then just try guessing stuff. So if n is 1, well, this thing becomes, oh my goodness me, e to the 2. Can I try to multiply it by 2 to the power of n, in this case 1? I do all of that stuff. So I multiply that, and then I divide it by something, n plus 1. Now I'm not sure how do I do a factorial in my calculator. Is there a way to do it? Wait, let me actually see. Is there a way to do a factorial in my, what was it? PI. How do I do a factorial? Probability. The whoops. Probability. Select factorial. Press enter. Oh, there we go. That's, yeah. Let's equate it. Yeah, so it's like 14.7. So that's a really high, very, very high error. Where am I at? What the? I'm lost. Yes, so 14.78-ish. Around there. If n is 2, let's see. Let's make these 2. Well, now it's 9.8. So it's actually gradually getting smaller. Okay, let's actually up it a bit. Let's do 5. Or let's actually do 7. It's really just a guessing game. 7. 0.046. There we go. Is this less than? Oh, shoot. That's 0.01. So we can't use that. Keep going. What if n is 9? This is just me picking out numbers. Yay! Got it. 0.002, which is definitely less than 0.01. How about an 8? Let me see. 0.0100425. Yeah, so this is still greater. So 9 is it. So we can take n equals 9. This is a plausible n, or we call it a good enough n. I'm not saying it's the right answer because I could do decimals, right? Let's just say it's a good enough n. Smiley face. Okay. So okay, cool. The ninth. What is this? Oh, what does that mean for us? Right? Like, so what? It means that, so this actually means when we're on the interval that we're looking for. So the interval was, what in the world? Negative 2, 2. Am I right? Am I wrong? Hmm. Okay. Apparently, I'm wrong. It says it provides a good approximation to negative 1 and 1, which is apparently the next item. I think it's just a graphing thing. Anyways, okay, we're just gonna say that this is just a fun fact. Okay, I'm not gonna go into it, but I'm just gonna say it pretty much. Basically, if we so the idea is that the better and better ends, right? The higher and higher ends we actually get a better and better approximation of the true function, which is e to the x, right? That's the idea. So the higher the end, the better the approximation. And apparently here, when we got n equals 9, that's a good approximation for e to the x in the interval negative 1 to 1, right? And then for f, whoops. Okay, there's a reasoning. I'm not going to go to the reasoning. Yeah, and then for the graphs, pretty much, yeah, I mean, it just gets better and better. I mean, I don't even have, I kind of showed it already in Desmos, but yeah, that's the idea. So maybe for my final words here, as n gets, or as n increases, we say that my Taylor polynomial approaches the actual true function. Yeah, so let's end with that. Anyways, I hope you guys enjoyed this video. I hope you learned a lot. And most of all, I hope you had fun. And I'll see you all in the next video.